Well, hello again. In the last video we introduced bipolar transistors. We looked at input and output characteristics for common emitter configurations. Then we considered biasing, the establishment of quiescent conditions. We looked at the reason for biasing and considered how an AC signal caused variations in currents and voltages around those Q or DC values. In this video, we're focusing on the effects of applying AC signals to amplifiers. The signal could be, for example, a little voltage variation that's produced from this microphone. We will develop an AC model for the transistor, a model that we can use to analyze amplifying circuits for such things as voltage gain or current gain. Okay, just to give you a little bit of a recap here, if you remember, in the last video we considered a circuit really very similar to this. The only difference is, and this was the first circuit that we'd actually considered to talk about really biasing and the effects of applying an AC signal, and therefore why do we need to bias, etc. Now in the previous case we didn't actually have values for these sources over here or resistors. So what I've done is I've put in some of these values here. Okay. Now if we wanted to actually work out the quiescent conditions for this circuit, well, how would we do it? Well, look, really as far as the base side is concerned, we'd need to find this base current. How would we find the base current? Well, we could simply take this little loop over here. Look, if I took that loop, it's a really easy thing to do, to take that loop. Well, what would I have? Well, I'm going up in voltage now. Let's look at the base current. The base current would be what? Flowing in this direction. Okay, I've got a voltage across that resistor plus, minus. We're also assuming that VBE, that's the base emitter voltage here, is 0.7. Okay, so if we went round the loop here, we would basically have what? Let's do it. Okay, I have a 20 going up. I have the drop across here, so that's a minus IB times 1.9 meg. And then of course I've got the drop of 0.7, all equals 0. I've completed the loop. Okay, so now the only unknown in this equation is IB, and if I care to solve for IB, taking basically the IB term to the other side, I've got 20 minus 0.7 divided by 1.9 meg is really equal to this base current IB, which is really approximately equal to 10 microamps. So that's the base current in that particular circuit. Okay. If you remember from before, we also looked at the case, well, what is the maximum collector current that can flow in this circuit? All right. Well, the maximum collector current would be when that transistor basically looks like a closed switch. So I've got 20 volts here. I've got a 10K resistor here. So really it's 20 volts divided by 10K would be the maximum collector current, which of course would be 20 divided by 10K is 2 milliamps. The collector current that we would calculate using IC is equal to beta times IB is simply equal to, I'll assume once again, a beta of 100. So that's 100 times this 10 microamp of base current, and that's going to give us 1 milliamp. So this is nowhere near the maximum collector current, so that was a valid relationship to actually use. Okay, remember the max was actually 2 milliamps. Using this equation here yielded a current of 1 milliamp. So we're well away from the maximum. If you wanted to find the voltage at the collector, that's that voltage there with respect to the common, which in this case is the same as the collector emitter voltage VCE. Well, that's pretty easy. We can say in this case VC is equal to VCE. That is in this case. That's not true if I had an emitter resistor here. But in this case, it is true. And so that's 20, okay, this voltage minus the drop across the 10K resistor there, which is 1 milliamp times that 10K resistor. That evaluates to 10 volts. And so really it's 20 minus 10, which means that VCE, which is the same in this case as VCEQ, VCE, VCEQ is equal to 10 volts. Okay? Now, I went a little further than this. I said, look, let's sort of show this picture graphically, what's going on graphically. And so what did we do? We established basically a load line. Okay, so we looked at the load line. All right, so if I look at the load line, what is the load line? Well, it was simply really a loop around here. Remember, let's just do this. That's IC plus minus across that resistor. We could now go through this, and of course plus minus, that's our VCE term sitting there. So if I do this, I'm just summing the voltages. I've got what? I've got VCE, I've got plus IC times the 10K resistor, and then a minus 20, really all equals 0, okay? Is that the load line? Well, not quite. That's the essence of it, taking the loop, but now we just simply re-express that as IC is some function of VCE. All right, so I'm going to just write that down. You can do this for yourself, just as a little bit of revision there. Just rewrite this equation as IC being equal to, and then it's VCE divided by 10K plus 20 divided by 10K. That is the load line equation. In order to plot this equation, we basically need to have 2 points, any 2 points. And the easy ones, of course, would be to choose VCE equal to 0. If that's 0, then what's IC? It's 20 divided by 10K, which is 2 milliamps. And in the other cases, make IC 0. If IC is 0, then VCE would simply be equal to 20. Okay? So that's the load line. Now, if we want to just have a quick look at that graphically and show this information on our graph, let's do that. Okay, here is our graph of IC versus VCE. All right, the characteristic curve that we are on is this one here, and that corresponds to having that base current, if you like, IB, which is really the quiescent value, IBQ. We'd establish that as being 10 microamps. Remember, it's a plot of IC versus VCE. Well, our load line, if we plot our load line on here, well, our load line is going to basically look like this, where this point here, of course, was 20, and this point over here was 2 milliamps, okay? Our operating condition, or quiescent condition here, is the intersection of that load line and the characteristic that we're on, which is this one right here. That gave us a VCE of 10 volts. And if we go over to the current axis, that gave us an IC of really 1 milliamp. Okay? And that was our quiescent condition. Okay? We took this a little bit further to look at the motivation for biasing. We said, okay, what if you apply, if you like, an AC signal to the circuit as well? So what we're going to do then is, as we did before, in series with this DC voltage here, we imagined applying a little sinusoid there, okay, plus, minus. That could be our signal. We could label that. We could say it's VS, okay? And then if you remember from last time, we said, okay, we imagined this little sinusoid going from what? Up to half a volt down to minus half a volt. And we looked at a couple of instances in time. We said, okay, when this is plus half a volt, we said that was one instant in time, let's say T1. We said, let's freeze time. What's the effect on the base current? Well, if that's 20 volts plus half a volt, the base current at that instant in time is now larger. It's a larger base current. What has that done for us? That has effectively moved us onto a different characteristic curve. So what we have is, due to that larger base current, due to the presence of that signal, it's as if we've moved to another characteristic curve, let us say like this guy here, and so we effectively have moved our operating point to, as it were, a new value at that instant in time when the signal source had reached half a volt. And so we have now what? A new value of VCE and, if you like, a new value of collector current. Okay? Then we considered the case where the AC source, okay, had actually reached a minus half a volt. So this little signal source here now, and if we were to just draw that to help you again, here's our little signal source. This is Vs, and remember we just considered this at half a volt, and we said, oh, maybe that corresponds to time t1. And then let's now consider the case where it's actually dropped down to minus a half a volt at, let's say, time t2. Okay, so now freeze time at t2. The little source over here is what? It's minus half a volt. So now what do we have between here and here? We have the 20, as it were, okay, plus a minus half a volt. So if we have a minus half a volt here, this voltage between this point and this point is actually what? It's actually 19.5 volts. It is not 20. So in other words, you could say now the base current at that time T2 is actually less than the quiescent value. Because this voltage between here and here is no longer 20, it is actually 19.5 at this time T2, due to our little signal source having reached minus half a volt. Now what does this do on our characteristics? Well, what is done effectively now is to really move us to, if you like, a different characteristic curve. Let's say this one right here, at that time t2. And so therefore it's as if our operating point has moved to this position right here. And therefore we have this VCE now. And then correspondingly we would have this collector current over here. Then we argued, okay, let's unfreeze time, as it were, and let that sinusoid go. What's going to happen? Well, we're effectively going to be seeing this operating point moving up and down the load line. And so what we're really seeing is a variation around the quiescent value for VCE. So actually VCE, the AC VCE, is varying around that 10 volts. And then of course over here, we've got a variation, as it were, in collector current around, centered around the DC quiescent collector current. And so we saw, well, biasing, it's important to establish the quiescent or the DC value really in the middle of this active region here, so we can have the maximum possible swing without distortion. Okay, so that's just a little bit of a recap on what we really said last time as a motivation for as to where we need to establish our quiescent conditions. So it is important that you understand that basically these AC voltages and currents are basically superimposed, as it were, around the DC values. Now what we really want to try to do in this section of material here is to be able to look at this AC effect, perhaps with respect to this effect over here, or look at the output IC current in relation to the input variation in IB, or the output VCE in relation to the input signal voltage. All right, now we know that they're superimposed around DC values, but it would make our life a lot easier knowing, yes, these values are superimposed around DC values, but for us to now just concentrate on this AC voltage, this AC current, and so on. In other words, just look at the AC effects, and in the back of our mind we know that they're actually operating around the DC values. Okay, so what we need to really do next is see if we can develop an AC model for the transistor itself, and then come up with an AC equivalent circuit that we can use to analyze a given amplifier.